cation exchange process, reverse osmosis process to prepare the demineralized water which we use in the power plants for the steam purity to avoid the boiler troubles, to avoid the priming foaming. All these are related in the power plant chemistry which we teach to our students. So certainly I think that secondly, corrosion is also another important part in the curriculum, which to avoid the damage of the turbine plants, boiler plants, to avoid thus we carry out the degasification of the water, which is to be treated in the boiler. We remove the CO2, we remove the O2, we add the coagulants, so all these measures which we teach there in the power plant, how they are being utilized in the power plant, our students, participants can also visualize. Lubrication is another part that just to avoid the damage of the turbine and the boiler tubes, etc. So to avoid the reduction of iron of the part to the iron oxide, we again use the lubrication for the smooth conduction of the machinery, of the turbine plants and of the boiler tube. So all these topics which we have in our curriculum for the PG applied chemistry students and for the BTech students are very much being applied in the power plant. Now, I am not going to take much time because our experienced expert, Soumitra Banerjee, is there from the power plant itself. I would like to have his experience of the power plant. But before that, I would like coordinator of the Kanchan Khare to give a brief outline of his biodata. Kanchan, please.
Thank you, ma'am. This is the brief biodata of our expert, Mr. Soumitra Banerjee, who is the alumni of Government Engineering College. He did his post-graduation from the Department of Applied Chemistry in 1985 with specialization in chemical process industry. Amongst his extended service record, he has given his valuable contribution by serving Asian Paints, Iron Exchange Services West Limited, Gujarat Power Engineering Corporation, Raymond Limited, Tata Power Company Limited, Adani Power Limited, Jindal Power Limited, Birla Soft Limited, Lalitpur Power Generation Company, and then he co-founded his own private limited, Industrium Solution Private Limited. In his experience encyclopedia, from all his exhaustive experience includes 25 years of his services in power plant chemistry audit, water audit management, water audit, power plant chemistry related problems related with fuel, water treatment analysis, problem rectification. He has great experience to analyze problems related with water lab, oil lab, coal lab, ETP cooling, water chemistry, stream water chemistry, condensate polishing unit, sensitive water chemistry, power plant chemistry audit, commissioning operation of complete power plant, corrosion management services. He has many awards and applauses in his working institution, and we are very much honored to welcome one great feather of our cap of JECN, who is also the alumni. Welcome, sir. I call upon Mr. Soumitra Banerjee to start his presentation.
Right, madam. Thank you so much. I'll start my presentation. Before that, I thank the management of JEC, Jabalpur Engineering College, my alma mater, in fact, to allow me to present my paper on recent advances in power plant chemistry. Before that, I thank respected principal sir of Jabalpur Engineering College, my current HOD, Sri S.K. Srivastava of Applied Chemistry Department, ma'am, respected ma'am Maheshwari, Anubhav Maheshwari, respected ma'am Shilpa Kare, and respected seniors and dear participants. Wish you a very happy Engineers Day. And whatever I learned in applied chemistry department by 1995 was being applied in the beginning of my career, and that has made me competent enough to get a job in different power plants. There's a topic chosen today into TEQIP 3, which is an initiation by Government of India and Technical Institute funded by World Bank for enhancing the skills and competency level so that, may I request all to mute please? And enhancing the skill and competency level and also to become self-reliant. This is a step towards India's self-reliance, where in today's lecture we will be seeing few of the significant changes in power plant chemistry, and those significant changes, if our upcoming students can take right now and can practice it in some time, they will be becoming better, and our reliance on different other countries will reduce. So, two humble requests before I proceed. One is, please keep your devices mute and till the question and answer level, which is at the end, and use the chat box instead to, where you have any question, and those questions will be summarized by the convener and the organizers, and they will be dealt with at the end. So here we go. This is the national webinar on recent advances in power plant chemistry, which is arranged by Jabalpur Engineering College, Jabalpur, under the TEQIP 3. And I am the alumni of Department of Applied Chemistry, Government Engineering College, Jabalpur, 1995 batch. I am the consultant of power plant chemistry and water treatment, and I am founder of JEC Solutions. And you have already heard my little bit of my career advancement, how did I do in the last 25 years. Going forward, the chemistry department in any power plant actually provides a skilled scientific services in order to improve the availability, efficiency. Most important part is efficiency. We do a lot of thermodynamic calculations and give the things to the management, the site management. And we also help the economics of generation. This department comprises of chemical lab for the analysis of water, steam, then reporting and data control. We do DM plant operations. We do maintenance and troubleshooting to cater and make up water for boilers. Then circulating water. We chemistry. May I request again to please keep your phones on mute or devices on mute, because I am getting background noise. Kindly hear to my request. My very humble and sincere request to please mute yourselves. Then we do chemistry control to optimize the cooling water and exchanger performance by reducing corrosion scaling and microbial controls. We also do the LPHP dosing for the steam water cycle control. Now there were subcritical plants when I passed out from the chemistry department at that time, and we were doing both LP and HP dosings. Now, now we have in India lot many supercritical power stations where HP dosing is eliminated, and the steam cycle goes into a single cycle. In both the phases will exist throughout the cycle. It will be a once-through cycle. There is no drum nowadays. Supercritical stations. Then thermodynamics. Our department talks about thermodynamics. We do a lot of heat transfer monitoring in cooling water system for condensers and heat exchangers. We calculate the thermal efficiency and heat transfer equipments in cooling water system, maybe a plate type heat exchanger or a shell tube type heat exchanger or a condenser. that is also our chemistry job, and all these things had been taught in applied chemistry department and still been a part of their curriculum. Then we do GCV balancing, and GCV balancing is very important for any power plant. What is the incoming GCV we had in this month, so many gigakilocalories we had, and how much of we burnt and how much is left. Now there is a big gap which we try to fill in with modern equipments and modern things, and that we will be also talking about during this program. So stay tuned, please. And we also participate in the new projects from the conceptual stage so that we understand water chemistry and their treatment requirements, and we do a lot of things about the treatment per se. You know, if the suspended solids are of some micron level, then what to do, and if they are very high suspended solids, then what to do, all those things. Then we are actually in this department, applied this chemistry department in a power plant, in a thermal power station, is actually responsible for the power plant chemistry department and sampling and analysis of fuels, interpreting the resulting data from the fuels, maybe it's a liquid fuel, gaseous fuel, or coal. We play a very important role in all the thermal power stations and also in the power stations which are. May I again request you to mute, please? May I again request you to mute, please? May I please request the organizer to mute all? बीच में आ रही है, please mute everybody. Ma'am, please force mute everybody. I know that, but again do that, please.
Yeah, I'm doing that.
Okay, ma'am.
Please carry on.
Okay. Now, we do sampling and analysis of fuel. Maybe it's solid fuel, maybe coal, maybe, and that also has been taught in applied chemistry department way back. And I remembered everything, all the proximate analysis and ultimate analysis, and I could fluently speak during the interviews about those things. So that is not a part of other chemistry curriculum. It is only there with the applied chemistry department. So that is, fuel chemistry, analysis of fuel and interpreting them, finding the GCVs through different methods, and then operating a pre-treatment and DM plan, which we will be talking about today, and quality control of raw treated feed water, cooling water treatments, technical control of demineralizer, monitoring and control of corrosion, which is a very important aspect in power plant chemistry. Then, if required, acid cleaning of these steam water cycles, managing the storage and handling large amount of chemicals. We deal with very heavy and large amount of chemicals in tons and tons. So, in big power plants, like I worked with 4,620 megawatts of Adani power station, there we had to do a lot of chemical handling, and also in Tata Power and also in LPGCL, there was a lot of chemicals to be handled. Then we do understand the ion exchange resin, and we do troubleshooting of that. And lastly, but importantly, the document and data control. This is our job in power plant chemistry, and this has been taught in applied chemistry department. And applied chemistry department makes people competent enough to handle the things when they join any power plant chemistry department. Now, the technology which we will be talking about today, the changes we will be talking about today from the past and the recent, is one is the technology incorporated in water treatment plant, that is one is time reduction in coagulation, completion assessment. We have to do the assessment of how much of coagulant and how much flocculant needs to be dosed to clarify the water, and we need to avoid overdosing or underdosing of aluminum or ferrous salts, and we will discuss why is to be avoided. And the conventional clarifiers has been now replaced by HRSCC and new generation clarity circular to reduce the capital cost, to reduce the area required, to reduce the time required for the water clarification, and that is a very big achievement in fact, and can be even used for other water treatment sections like municipalities. Now, we will also talk about the reverse osmosis with now very high yield and advances in membranes, a little bit of it. We'll talk about a new thing which has now replaced mixed bed deionization, is electro-deionization, which is a very, very recent development, and it's coming up in India now very well. And then we'll talk about the advanced filtration technologies, why they are required, and how it is to be used. We'll also talk about the technology incorporated in rectification of problem in steam water cycle. Though FAC is flow accelerated corrosion, though FAC has been recognized a bit late in India, but ultimately it has been recognized, and there was the evolution of AVTO and AVT oxygenated treatment started in Germany, Japan, US quite earlier than us, but we have understood corrosion. Again, somebody please mute. Please mute. Yeah, thank you. Then this FSC is what is FSC, and how this has come, because earlier we only talked about development of magnetite layer, that is Fe3O4 layer as a protective layer in the boilers, but that concept has changed. Now that concept has changed to oxygenated treatment. How it has changed, we'll talk about that. We'll talk about the newer things which has come in the steam water circuits, like cation conductivity and D-gas cation conductivity, introduction of color changing resins in cation conductivity and D-gas cation conductivity. Then we'll also talk about the reducing time and reduction of human error and increasing safety during cold sample by introduction of auger and automatic samplers. And we also, lastly, will talk about reducing time and human error in cold analysis, like online GCB, ash and moisture analysis, and thermogravimetric analysis. We may not be able to take care of the lubricants and their advances today in the short span, but in future we will be taking it. Now we try to understand with this that what applied chemistry department teaches at the first and what we employ in the plants at the first step. So before that, I have to go into the settings and change the audio settings.
When you think about it, water is pretty amazing. It falls from the skies and flows through our taps in an endless water cycle that lets us reuse the same water over and over again. And from sky to tap, it all begins with a single drop. It's Welsh Water's responsibility to keep 3 million people healthy every day with safe and reliable water. We draw water from our rivers and reservoirs before cleaning it and supplying it to millions of homes and businesses throughout Wales. But have you ever wondered how clean drinking water reaches the tap? To make sure it's safe for us to drink, we need to clean 800 million litres of water every single day. And it all happens in our water treatment works. The first part of the process is called screening, where we remove large debris like leaves, sticks, and bits of plastic. Then the water moves to the next stage, which is called clarification. Chemicals such as ferric or aluminium sulfate are added to the water as well as pH correctant if needed, such as sulfuric acid or lime soda, which react with the impurities. When the water is stirred, the chemicals cause all the impurities to bind together to form thick clumps called floc. This makes it easier to remove them from the water. In some water treatment plants, the floc settles to the bottom, where we can take it away for further treatment. In plants like this one, we pass fine bubbles of air through the water. The air bubbles stick to the floc, making it float to the surface where it forms a thick crust. We can then scrape this crust off the surface of the water and take it away to be treated. Sometimes it's necessary to add chemicals such as caustic and lime soda, as well as sulfuric acid, to adjust the pH of the water, which controls the level of acidity in the water. The water now flows to the next stage of the cleaning process, which is called filtration. Here we filter the water through a mixture of sand and gravel, which traps all the tiny impurities. When enough of these particles have been gathered, we clean the filter by forcing water or compressed air up through the filter bed to loosen the trapped dirt, which we can then take away to treat it. In some treatment work, such as upland reservoirs, we might filter the water a second time to make it as clean as possible before it goes on to the final stage. This is called disinfection, where we kill harmful bacteria and all other pathogens that could cause stomach upsets. We do this by adding chlorine to the water like in a swimming pool, just enough to make the water safe while still leaving it tasting fresh and good to drink. By now, the water is treated and cleaned, and it's ready to flow through our 27,000 kilometres of pipes to your homes and businesses. And just think, it all started with that single drop falling from the sky.
So this was about the water treatment plant, which normally we get drinking water, and the same process is also applied initially in the power plants. The first thing is the coagulation and flocculation. Though in this movie, the short video, you saw that the tiny air bubbles are pushed in the water so that the flocks are coming up and they are skimming it. In India, mostly it is the opposite, that we add coagulants and flocculants to settle down the suspended particle matters, but we seldom add any air to it because we have less oil and grease. Wherever there is high oil and grease, there we have to add air so that the air makes the sludge to come up and we can skim it. Now, regarding coagulation and flocculation, this facility actually is for removal of solids and turbidity and colloids, and you are already using alum in most of the cases. Like in Jabalpur, if you see, in Jabalpur Nagar Nigam, they are using ferric alum in the dosing area, and then they are doing the clarification and flocculation. This brings about the settling of the substances to their removal. And for effective removal, particles are to be aggregated to large settle level solids. And this is being done by addition of chemicals, which are known as coagulant, because the process is known as coagulation. So this process normally takes four main category or main types of coagulants: aluminum sulfate, that is ferric alum, alum or non-ferric alum, filter alum. Then polyaluminum chloride, which is an advancement about since 20 years. This is working well and not reducing the pH as much as alum does. Ferrous sulfate is another one which we use wherever the membrane processes are there in the downstream equipments. And ferric salts are also used where membranes are there in downstream equipments. So we saw that what is water treatment till now. Now we'll see what is the mechanism of this coagulation.
Natural particles in water have negative charges that repel other material and thereby keep it in suspension. In coagulation, positively charged chemicals are added to neutralize or destabilize these charges and allow the particles to accumulate and be removed by physical processes such as sedimentation or filtration. Commonly used coagulants include aluminum and iron salts and cationic polymers. Flocculation, the water treatment process following coagulation that uses gentle stirring to bring suspended particles together so they will form larger, more separate clumps called floc. Sedimentation, a treatment process using gravity to remove suspended particles. Filtration, the removal of suspended materials in a fluid stream by passage of the fluid through a filter. And flocculation, agglomerate turbidity into larger, heavier particles that can then more easily be removed by sedimentation and clarification before filtration. Filtration is typically accomplished using rapid sand or mixed media filters, but slow sand filters are still in use in some areas. Likewise, newer technologies, including different types of membrane filtration, are also available to utilities. For the purpose of this program, conventional coagulation, flocculation, sedimentation, and filtration processes are illustrated for the removal of particulate matter from turbid waters. The particles that cause turbidity consist mostly of non-settlable solids. These particles typically do not settle out of water because of two factors: particle size and the natural repelling forces between particles.
So, can you please mute? Thank you. Now, if you see that the coagulation process itself says that negatively charged particles are to be agglomerated by addition of positive ions into it, and those positive ions are given by aluminium and or ferrous sulfates. Maybe some covalent aids are also used sometimes. Now, we were doing jar test analysis to do the assessment. We are talking about the assessment of coagulation, flocculation, how many ppm, how much ppm of the coagulant like alum or ferric chloride has to be dosed into the water, and how to assess that, okay, this is what we have to do and this is what is required. Now, this was a very tedious process, and this is still used in many plants, and it's a very tedious process. Like what we were doing in chemistry department, that we were drawing around 20 liters of water from the raw water source, and then we were coming to a lab making solutions of coagulant, 1% solution of coagulant, and then 0.1% solution of flocculant. Then, in these jars, we were taking water, and in one of the jars, we were taking water, but we were not adding anything. Now, we allowed the mixture to go the Rekaram speed, the flash mixture speed. We allowed these speeds to match the flash mixture speed, whatever the flash mixture speed is. No, maybe. Please please mute. I request again and again, please mute. This is quite disturbing if you are not muting your devices. I have requested you humbly and sincerely before that please kindly mute your devices. Or otherwise, organizer, please mute all and then I will unmute myself. Right. So what I was talking about, that this process of jar test is very tedious. One is drawing the water from the source, about 20 liters of water, we bring in the lab and then making 1 liter each in the jar. We keep 6 jars, 1 jar. The stirrer is not put, the other jar the stirrer is put, and the stirrer is then run at the same speed of what this our flash mixture is working. Now, flash mixture speed is governed by the liquid density and the suspended solids in it. So, flash mixture speed is maintained here, say about 100 to 150 RPM. Sometimes it goes to 300 RPM. So, that flash mixture speed is maintained here, and then some ppm of the coagulant is added. Say the first jar, you see, the first jar maybe 6 ppm, second jar 8 ppm, third jar, ppm means milligram per liter or milligram per kg, parts per million. So in the first jar maybe 6 ppm, second jar maybe 8 ppm, third jar maybe 10 ppm, fourth jar maybe 12 ppm, fifth jar maybe 14 ppm, likewise. So we keep on adding the coagulants, and we run the stirrer at the speed of what our flash mixture runs. Again, somebody has unmuted himself or herself. Thank you. So, when we use these jars at different at flash mixture speed, we run it for 1 minute at flash mixture speed, and at the vortex we add the coagulant at say 6 ppm, 8 ppm, 10 ppm, 12 ppm, 14 ppm, and then we run it for 1 minute and we then slow the speed as per the flocculator. We have to be there for say 30 minutes at the flocculator speed, and then we have to stop the flocculator speed or run it at very slow revolutions per minute RPM, so that we can simulate the whole system of our clarifier. Normally this was taking 6 hours because we have to do 2 sets. One set is for coagulant, another set after selecting the coagulant ppm you have to do for flocculant. And this is how we were doing it, and I will not run the sound with it. You just see what is written and how the process goes on.
Making water safe is the job of every water provider, and doing that job requires constant monitoring and operational adjustments. Water supply operators make seasonal, weekly, and sometimes daily changes of chemicals and chemical dosages to respond to fluctuating raw water conditions. The goal? To produce the best water possible. To mimic the effect of any changes or adjustments on the water supply, operators use jar tests. It allows them to see what the results will be in the laboratory and predict what will happen full scale without affecting the operation of the plant. Jar testing is an invaluable tool, but can be difficult to perform correctly. When accurate results are generated and correctly applied, jar testing can translate into better treatment and more optimized chemical dosing. Jar testing is something operators should perform routinely in case there are unexpected water quality changes. Some plants do daily jar testing, so the operators are prepared. The most common use of jar testing is to determine the appropriate use and dose of chemicals in water treatment. The objective of water
Now, as you saw in the video, the process is quite tedious, and we need to be very sure about addition of coagulant and flocculant in the system, because overdosing will create a carryover of either aluminium or iron. Aluminium will go and go into the reverse osmosis membranes and do an irreversible scaling in the reverse osmosis membrane, which cannot be removed by any method, and it can also form aluminum silicate in the condensers and heat exchangers. Whereas the iron also goes into the membranes, reverse osmosis membranes, and can foul the reverse osmosis membranes, and it can also go and settle down in the cooling water system somewhere and can cause microbiologically induced corrosion, as under the deposit of iron there will be a lot of anaerobic condition, and a bacteria called desulfovibrio gets generated over there. Now this tedious process has been replaced by a new process called measurement of zeta potential. We'll again see a video about the zeta potential. Zeta potential is actually streaming current meter. Zeta potential is the charge of negative particles. It's a measurement of charge of negative particles. So if the water is dirty, you may be having minus 20, minus 30 kind of zeta potential, and when you keep on adding the coagulants, it will tend towards going towards zero. So we maintain minus 1 to minus 4 as an excellent condition, so that we do not have to do the jar test and we can find out what is the dosage is required for the optimum conditions of coagulation, and that is very quick. This video will illustrate to you what is zeta potential and how it is done, and it is a very good advantage for the situation because it will avoid the overdosage and underdose of coagulants. Underdose will cause carryover of suspended particles. Overdose will cause carryover of coagulant chemicals, and then carryover not only causes high cost of the chemicals, but it causes problems in the downstream equipments. So let us see this video once again. Let us see this video and let us find out how quickly we can.
Well, here I want to talk more about the coagulation process. And for illustration purposes, I have 4 jars that have negatively charged colloidal matter in each of them. All of these particles carry the negative charge. They repel one another, and that repulsive force is called zeta potential. And the zeta potential can be measured to determine the extent to which the particles are carrying a negative charge, or the negative charge within the solution. Well, in order to overcome that zeta potential so that these colloids can come together and form
सर आवाज नहीं आ रही है वीडियो की आप अनम्यूट करिए अपने आप को शायद तब आएगी
where we have the different maximum, excellent, fair, and poor. So starting at the negative charge, they repel one another, and that repulsive force is called zeta potential. And the zeta potential can be measured to determine the extent to which the particles are carrying a negative charge, or the negative charge within the solution. Well, in order to overcome that zeta potential so that these colloids can come together and form microfloc and then macrofloc so that they can ultimately settle out, we need to neutralize the negative charge. So we do that by the addition of positive ions. And aluminum sulfate, for our purposes here, will be what we add. So when we add the alum to one of these jars, we see that positive ions from the alum react with the negatively charged colloids, and that effectively neutralizes the charge. So we call that step charge neutralization. Now that takes 1 to 2 seconds to occur. So once we rapidly mix the coagulant in the solution, within 1 to 2 seconds, we've achieved charge neutralization. And there's different degrees of coagulation. This is how we classify the extent or the degree of coagulation. And it's based on the zeta potential. Well, here you can see this chart in the upper left-hand corner where we have the different degrees of coagulation being maximum, excellent, fair, and poor. So starting at the bottom, poor coagulation would be if we had a zeta potential in the range of -20 up to -11 millivolts. As we lessen the negative charge, as the negative numbers get smaller, for example, going up to fair, going from 10 to -5, that's considered fair coagulation. And then as we further reduce the zeta potential to -4 to 1, or a range of -4 to 1, we consider that to be excellent. And most plants will operate slightly negative here. So this excellent degree of coagulation is where most plants operate because they don't want to add too much coagulant because it can then pass through the plant and end up causing issues in the distribution system. And then our final classification of maximum coagulation is when the average zeta potential is in the range of 0 to +3. So you might want to remember that for your exam, the different degrees of coagulation. Well, now that we've neutralized the charges, there's this thing called van der Waals forces that come into effect. Now, van der Waals forces is the force between all objects that tries to pull them together. So it's not until van der Waals forces overcomes the zeta potential that these colloids can come together and form a flock. So by neutralizing the zeta potential, van der Waals forces can then go into effect and our microflock can become macroflock. Additional chemical in the form of polymer, and a cationic polymer is typically used in the coagulation process, and that helps keep that flock together. Flocks gently mix and collide in the flocculation process. They get even larger, and then ultimately they'll settle out in the sedimentation process. So to kind of give an idea of how this process works, on the far left, we start with charged colloids that are repelling one another due to the zeta potential, and they will not come together. Then in the next jar, we see that coagulation occurs once we add the aluminum sulfate or whatever the coagulant is that we add because of the addition of positive ions. Then in the next jar, we see flocculation begin to occur, where the microflock becomes macroflock and even larger so that it can then settle out. And in this final jar, we see the sedimentation process. So this is a brief overview of what happened.
So this is how the first thing which came that in the picture that we have replaced this jar test process which was taking 6.5 hours with the zeta potential meters. These meters are like simple conductive meter or pH meter which tells us the how much negative charged particles are there in the system. Now, since the time is a constraint, I can't take you through the coagulation field, but I will take you in our next program through JEC. So the point over here is, earlier the optimum conditions for coagulation floculations were time intensive. It was taking 5 to 6 hours. Now zeta potential, the streaming current does it in seconds. Now, about the clarifiers, this is the second point which I wanted to emphasize on, that we were using conventional clarifiers earlier, and still, if you see all the municipalities, most of the municipalities have these kind of clarifiers where water mixed with coagulant is fed into the center of the clarifier and goes down, and it slowly settles down here. It is having a raker arm below. These are called raker arm, which pushes the sludge, whatever is formed towards the center so that it can be drawn off. And it was having skimmer as well, because sometimes overdosing of coagulants like alum and all can break down the bicarbonate alkalinity, and CO2 can form, and that CO2 will be trapped in the sludge, and the sludge can go up in the topmost layer. So that skimmer will work, and skimmer can take care of the sludge, take out the sludge from the system, and there was also scum drop. Now the downside of these clarifiers were, it was the detention time of these kind of clarifiers were 4 to 4.5 hours. Thus, the area requirement was very high, and the capital cost for the civil and mechanical structures were also very high. But this has been replaced by something called HRSCC, which is also known as high rate solid contact clarifier, which is particularly very useful when you want to remove colloidal silica from the water by addition of either dolomite or dolomitic lime or Mg or magnesium oxide. It reduces about 80 to 90% of colloidal silica and also reduces some of the silica. Now this HRSCC is something which has taken up in the year 2003, 2004, and it has come into existence for the colloidal silica removal and heavy metal removal. The advantage of these HRSCC, I'm going to show you the photographs of those HRSCC. The advantage of those are it produces treated water of highest quality with minimum time, space, and even your chemical consumption is reduced by normally 70%. In the high rate solid contact clarifier, these coagulants and large quantities of recirculating sludge are thoroughly mixed with each other in the draft tube, and then finally, in a slow mixing zone, it has been flocculated, and in the final sedimentation zone, it is sedimented. Here, we'll go with the photograph. Yeah, this is the advancement where the difference between the conventional clarifier and these clarifier, two biggest difference. One is the detention time required has now reduced to 2 to 2.5 hours. Means half the time is required. That means half the area is required and half the capital cost is required as compared to those conventional clarifiers. Second is the chemical dosing and chemical requirement are also lessened because this takes up the already formed sludge and tries to mix it with the sludge. Here there is an impeller, a kind of turbine which revolves at 25 to 50 RPM, and there is a VFD above, and the flocculant is dosed into this so that it mixes rapidly. This area is known as rapid mixing zone, and it then goes into the slow mixing zone where flocculation takes place, and finally here the concentration increases, the sludge concentration increases, and this is known as sedimentation zone. This is the more accurate picture. You will understand that the influent is coming here in the draft tube. This draft tube is having this impeller which runs at 25 to 50 RPM, and there is a variable frequency drive at the top of it, which you can operate based on your influent flow. And then after mixing with the sludge, already formed sludge from the bottom, it falls into the slow mixing zone where the flocculation takes place, and then from the bottom of the slow mixing zone, it goes up, it rises up, and the sedimentation will happen over here. And these are the radial launders, they call it. We call it radial launders, and this may be connected to a circular launder or a simple pipe. And this is facilitated with 4 of the sample points where we can know what is happening in which zone of the system. And this is good, but above this there is another thing which has happened. This is a plate type clarifier where the time is reduced, but combining this plate type clarifier and this conventional clarifier, the recent advancement is making of this clarity tube settlers. These clarity tube settlers are, like conventional clarity flocculators, having flocculation zone in the mid, but these plates or tubes are inserted just below 1 meter of the water level, so that water rises through these tubes and this sedimentation goes faster. So here is what is written: the tube settler and parallel plates increases the settling capacity of circular clarifiers. These are circular clarifiers having these tubes inserted within it, and this reduces the overall time taken, and also this reduces the chemical consumption, and it reduces the detention time from HRSCC, which was 2 to 2.5 hours. In clary tube settler, it has become 1.45 hours to 2 hours. So clary tube settler works well even at the very high flow rates, and it is giving quite a good results. Even it can go without monitoring for hours together. These vessels are tube settlers which can operate 2 to 4 times of the normal rate of conventional clarifiers basins. It is possible to cut covalent dosages up to half with these type of clarifiers, and new tube settlers can be designed smaller because of the increased flow capacity. And this, from the top, it looks like conventional clary floculator. Here is the flocculation zone, and this is the sediment retention zone. You can't see the plates in this picture here. The tubes below this water level, it is about 1 meter below this water level. These kind of tubes are inserted, and if you see inside, it will look like this. These kind of tubes are inserted below 1 meter of the water level. This is the top water level, where the clarified water is going to the launders, and these are the tubes which are inserted inside these circular clarifiers. So this makes a good advantage, and now in India we have even 4,000 meter cube per hour capacity clarifiers being used into big power plants, the supercritical power plants. Now the third point which comes is conventional clarifiers, conventional filters. Now conventional filters, we know about pressure sand filter, we know about dual media filter, we know about multi-grade filter, and those are having some disadvantages, like these are not continuous. The conventional filters are actually not continuous. They are having some or other problem, like whenever the DP has to be monitored, whenever the DP means delta pressure, the delta pressure when it goes high, maybe somewhere it is limited to 0.5 kg per centimeter square, somewhere it is limited to 1 kg per centimeter square. Whenever it goes high, we have to backwash. So it needs constant monitoring. It needs a downtime for the backwash and rinsing. The conventional clarifiers conventional filters were requiring downtime for backwash and rinsing, and conventional filters requires constant monitoring. Plus, a water wastage of 10% is there with the conventional filters. Any filter you take, a deep media filter, a multi-grade filter, or a pressure sand filter. Now, these are being replaced by other kind of filters, and now I can proudly say that this is now made in India by Gopani in Ahmedabad, and here is a video on these kind of filters.
Cleaning filters are widely used throughout the industrial, irrigation, and municipal markets for automated suspended solids removal. Force's fully automatic filters remove suspended solids from raw water sources and protect downstream equipment. Filter screens are available with mesh sizes ranging from 5 to 4,000 micron. Screens are constructed from high-grade stainless steel alloys and made in configurations that best address the types of debris in the water, such as sand, silt, fibers, and organics. Individual filter models are designed to handle flows from 10 GPM up to 7,000 GPM. In higher flow applications, filters may be used in parallel for limitless capacity. Forsta self-cleaning filters are suitable for systems with pressure ranging from 15 to 150 psi. Using system pressure, filters perform a fully automated cleaning cycle that does not cause interruption to main system flow.
Another advantage of these kind of filters were that you can decide upon what micron up to what micron you want to filter. So 5 micron, 10 micron, 15 micron, 20 micron, and so on. Whereas the conventional filters like pressure sand filter or multi-rate filter or dual media filter cannot filter below 40 or 50 microns. Pressure sand filter can do the filtration up to 40 microns and not below them, and the multi-grade filter and dual media filter can filter up to 50 microns. And remember, here is a very important catch that our eyes are capable, the human eyes are capable only to see up to 40 microns, not below them. Another type of similar system, because here the media is stainless steel, porous stainless steel, where the pores are made as per the requirements. Another video will show you how it is. I will not change the voice setting because there is no voice behind this. Here is the structure of, how it is made. This is another kind of same continuous filtration system where we can have filtrations up to certain microns. Here is that mesh which is reusable. And this is the housing, tri-motor housing, stainless steel reusable filter element, and spoken wiper system inside, and the oversized discharge. And you see how it is work. How does it work? And this also remains continuous. It works continuously, removes the suspended solids continuously. Once the suspended solids gets heavier, the suspended solids will go down, and once there is some pressure, it will open up automatically, and then it is controlled by filter management system, which draws this water while on the other hand, the filtration continues. That does not stop. This does not require any kind of monitoring. Now we go to the other part, that after we remove the suspended solids and we do chlorination, or we do now chlorination is being replaced by chlorine dioxide in many cases, and if time permits we will discuss on chlorine dioxide as well. But here are the processes which are normally employed for removing the dissolved solids. Now we have removed the suspended solids in clarifier and filtration system. Now it's time to remove the dissolved solids. Now dissolved gases will be either removed some part of it in the pre-treatment process, and finally it will be removed by deaerator in the power plants. For dissolved solid removal, TDS, we employ first is ion exchange. IX is ion exchange method, which is actually a chemical method where the field TDS can go maximum up to 1500 and the product TDS may be lesser than 1, but nowadays, as per the requirement by EPRI and BGP, these are two guiding principal companies in the world who tells what should be the specification of the water. Now, we are employing a mixed bed or EDI after the DM plant on RO to get a product TDS of less than 0.1 microsiemens conductivity. And most of the time we get a resistivity of 18 ohms. Now, after the ion exchange, there was electrodialysis process. Now it is not used as it is electrodialysis earlier. Now it is having some membranes also inside, and it has also gone for a revival. So in electrolysis process, earlier we could take 3000 ppm of TDS in the feed, and the output would have been 5 to 10% of the feed TDS. And then the reverse osmosis, which is pressure-driven system, can take up to 40,000 feed TDS. Now some membranes got developed recently for taking 44 to 46,000 ppm of TDS. This is employed for brackish water and RO water, and wherever the TDS is high enough, we take reverse osmosis membranes. We're going to talk about on this. And the product TDS is 1.5%, 1 to 5% of the feed TDS. And we normally try to maintain it below 3%. And finally, there is a process called multi-stage flash evaporator, which is a thermal process for removing total dissolved solids, which can work even at high feed TDS of 70,000, and the product TDS is only 5 to 10,000. Now we talk about this recent advancement of high recovery reverse osmosis system, because the water demand has increased, and earlier the reverse osmosis membranes were given only those which were employed for desalination. At least they were giving 30%, then 40% recovery of whatever water. Recovery means if I push 100 liters of water, only 30 liters or 40 liters were becoming desalined. Even still, it was having a lot of salts in it, but desalination was taking place with 30%, 40% recovery. And then in the decade of 2000 to 2010, the membranes developed were having about 50% recovery. Now there are very high recovery membranes available, and even 99.5% of the inlet TDS can be removed. Now, how these membrane works, let me show you one video, and you will understand. This is how a reverse osmosis, high recovery reverse osmosis plant may look like. This is a small plant though. In India, we have very large plants of these kind of reverse osmosis. BPCL Kochi is having 1000 meter cube per hour plant. Then HMEL means Batenda refinery is also having huge reverse osmosis plant. And Chennai, wow, Chennai is having a lot of desalination plants, maybe now 4 of them, and they're working on this principle. You just watch out this video and then write down the questions with you so that we can discuss it.
Water recycling plant processes purgatory wastewater after the ultrafiltration process.
You saw how this reverse osmosis system works, and now the recovery percentage has gone as high as 80%. And in some cases, when the field water quality is very good, we also go up to 90%. We can design it very well in India, within India. One challenge is here that we are still not able to make that polyamide layer in India. Now, making India progress needs somebody to make this polyamide layer, the top thin 0.2 micron layer in India. We are still importing that layer from outside, maybe US or Europe, and earlier we were doing it from China. So now, in Kochi refinery, there was some talk that they are going to make a plant which will be making this kind of polyamide and all. But this is a very good opportunity for Indian industry to create something which needs a petrochemical plant to work on to create that polyamide layer, and that polyamide can be made in India, and then we will be making the whole RO membrane in India. We are just rolling the RO membranes right now in India. So this is a point which I want to take here because we have some lagging, and then we go into these are some applications of membrane filtration. There are microfiltration, ultrafiltration, nanofiltration, reverse osmosis, then electrodialysis, and we are going to talk about electrodialysis. Now, another change which has happened in recent past is earlier we were using sodium zeolite resin or sodium cation resin for water softening, which was taking calcium and magnesium and was releasing your sodium in the water. So that was also increasing the conductivity of the water, and sodium is not so good as far as corrosion is concerned. So now nanofiltration is taking place, and the water softening through nanofiltration, where only divalent or multivalent atoms are separated, others remain in the water, is being used for water softening. Now, in the membrane process, there are advancements from polysulfone kind of layer. We went to PVDF, polyvinyl, then we went to PP, polypropylene, and now Teflon is the material which is used as a cellulosic material, more robust than cellulosic material, and that becomes a very good membrane in case of membrane separation. And these are some kind of membranes which are now being used as a submerged membrane, where water is being filtered in situ in a vessel where both filtered water and unfiltered water can exist. And we can talk about this little if the time permits. Otherwise, these are something which is quite recent and being vastly used in effluent treatment systems. We are not talking about power plant. When we talk about water treatment or effluent treatment, then we'll talk about the submerged membranes. Now this is EDI, electrodeionization process, where now resins as well as membranes, both are used together to remove the cations and anions, to remove the dissolved solids in the water. Conventionally, we are using either a DM plant having strong acid cation resin vessel removing removing cations, and then we were using degasser which was reducing the CO2, and then we were using anion resins, strong acid anion resins, or in conjugation with weak acid anion resins to remove the anions from the water. And then finally we were using one mixed bed, which was comprising of anion and cation resins. And these resins, when they were getting exhausted, they had to be stopped, one, and then you have to do a lot of chemical handling, because cation resins are regenerated with 5% of HCl, and anion resins are regenerated with 5% of caustics, NaOH. And in mixed bed, we have to separate out both the resins and do the regeneration either in situ, in that vessel separation, or we can take an anion resin in another vessel and cation resin in another vessel and do the regeneration. So it was taking a lot of acid handling, caustic handling, a lot of unsafe acts, and it was not continuous and needs to be monitored at all the time for sodium, silica, and other things, and even the conductivity which was required at 0.1 for high pressure boilers and power plants. So now we'll watch a small introduction about EDI, which is the recent advancement in the system, and we will try to understand. If you have any questions, write it down.
CEDI technology removes ions from water using a unique combination of ion exchange membranes, ion exchange resins, and electricity. The ion exchange resins are continuously regenerated without the need for regeneration chemicals. To understand how the patented ion pure CEDI technology actually works, let's go down to the molecular level and take a look at some water containing ions. Water contains positively charged cations, represented by plus signs, and negatively charged anions, represented by minus signs. When a pair of electrodes is inserted and an electrical current applied, the electric field drives the cations in the direction of the cathode, and at the same time drives the anions in the opposite direction, toward the anode. When we insert an ion exchange membrane made of cation selective resins, it will block the flow of anions and water molecules. Only cations will be able to pass through to the other side. When we insert another ion exchange membrane, this time made out of anion selective resins, it will block the flow of cations and water molecules. Only anions will be able to pass through to the other side. This configuration of membranes and electrodes forms the framework of a CEDI module. This process is limited, however, by the slow speed at which ions move through water. In effect, the low conductivity of water impedes ion removal. In other words, as the product compartment water becomes more and more pure, the electrical resistance of this water increases and counters the effect of the electrical field. Ion Pure CEDI technology solves this problem by sandwiching a mixture of cation and anion selective resins between the two membranes. The large surface area now offered by the resin beads effectively eliminates the ion diffusion resistance and allows the ions to move freely, even in ultra-pure water solution. The surface of the resin beads acts as a conductive path, effectively acting as a bridge for the ions to move quicker toward the membrane surface, faster than if they were in water alone. Taking a step back to look at how an ion pure CEDI module is constructed, we can see that if we move the electrodes farther apart and continue to add resin beads sandwiched between the cation and anion selective membranes, we create a series of water purification compartments, alternating with compartments where the ions are concentrated. As feed water is pumped into the system, it is diverted into separate compartments, namely the concentrating compartment and the purification or dilute compartment. These water streams remain separated throughout the process because only ions can pass through the membranes. Ions migrate and accumulate in the concentrating compartments, where they are washed away into the reject stream.
The water leaving this compartment contains a concentration of ions approximately 10 to 20 times higher than the original feed water. This water may be drained, recycled, or reclaimed for further treatment. At the top of the purification compartments, the ion concentration is at its highest. Here, the surface of the resin beads acts as a conductive path, effectively moving the ions to the membrane. At the lower end of the purification compartments, where the ion concentration has been reduced to the parts per trillion level, the electric field becomes concentrated between the resin beads and the surrounding water. When this localized voltage potential exceeds approximately 0.8 of a volt, an electrochemical reaction occurs, and water molecules are split into hydrogen and hydroxide ions, which are essentially acid and caustic. The acid and caustic generated in the module regenerate the resin beads by replacing other trace ions remaining. The attachment of hydrogen and hydroxide ions to the resin beads is exactly what happens to resin beads when acid and caustic are used for regeneration in conventional deionization systems. As a result, ion-pure CEDI systems do not need chemicals for regeneration. The electric potential does all the work. You essentially have a worker and polisher combined into one unit, which constantly regenerates. And ion-pure CEDI systems are more effective than other electrodeionization systems when it comes to removing dissolved materials such as salts, acids, and bases, as well as weakly ionized materials such as dissolved organics, silica, boron, and carbon dioxide. This continuous regeneration process also eliminates pH shock and greatly extends the life of the resins.
Now, the difference between the conventional DM plant and this plant is, EDI is we need not handle any chemical anytime. The simple and continuous operations, chemicals for all regeneration, chemical handling, unsafe conditions are eliminated. This is cost-effective operation and very low maintenance and low power consumption. And it requires few automatic valves, very few automatic valves. Only one downside, suppose this EDI, electrodeionization process, is subjected to calcium and magnesium, scaling can occur within this system. But not at low concentration, but high concentration will definitely make this EDI to clean it with proper chemicals then. So nowadays, what is happening, that downstream any reverse osmosis plant, because reverse osmosis plant removes all the hardness, or downstream a conventional DM plant, rather than putting MB, people are putting this EDI, electrodeionization unit, and getting the output conductivity as 0.06. 0.06 is quite equivalent to 0.06 micromoles per centimeter, while which is equivalent to 18 ohms per centimeter. Now, steam motorcycle chemistry advances, as I was talking about, flow accelerated corrosion, though it was being recognized in Germany, in Japan, and also in US in 1986, and they worked upon this flow accelerated corrosion. In India, till 2011, we were novice about it. And this change in 2011 of that year, and we actually changed a lot of things as per APRI. The flow accelerated corrosion is actually a metal loss that occurs in carbon steel equipments, and this occurs at low temperature, especially in pre-boiler systems, or especially in the systems where temperatures are low, like drains and all. And where what happens is the oxide layer, earlier we were removing oxygen and keeping oxygen levels below 7 ppb, parts per billion. So when we were keeping oxygen below 7 ppb, magnetite layer was getting generated through Hecourt's reaction. When magnetite layer generation was happening, magnetite layer generation was good, above 300 degrees and so on. But below 300 degrees, especially between 150 to 250 degrees centigrade, the magnetite layer is susceptible of FAC, flow accelerated corrosion. And it was actually then recognized by NTPC also that this is an industry-wide problem, and they have slowly moved. And this is, for last 50, 60 years, we were using hydrazine or sodium, that kind of reducing agents, mostly hydrazine in our system to help producing this magnetite layer, black colored Fe3O4 layer. But now the system has changed because FSC, flow accelerated corrosion, the number of incidents increased even in India. And this happens mostly between 120 degrees and 205 degrees centigrade. In high pressure boiler cycles, this temperature exists in the low pressure or intermediate pressure sections, and the pre-boiler section, economizer, a deaerator, then after deaerator, the economizer and the pre-boiler section is quite susceptible, and the header drains and the exhaust steam drains, they were quite having this FAC. FAC induces metal dissolution. FAC, flow accelerated corrosion, is actually a corrosion, not an erosion. It dissolves the metal due to the flow hydrodynamics. Okay, we'll see a picture to understand, though that picture is not very sharp, not a very sharp image, but at least you would be able to understand from this. See what was happening, that due to low oxygen and temperature and due to hydrazine being reducing agent, magnetite layer, Fe3O4, was forming. But due to flow hydrodynamics, this magnetite layer was getting dissolved in the flow. Especially it occurs when the pipelines are narrow and the velocity is high, more than 4 meters per second. So when it was dissolving, again the magnetite layer was forming below. Slowly then that was also getting dissolved, and then it was again forming magnetite layer, and then again the magnetite layer was getting dissolved. So this was a simplified system of the mechanism of flow accelerated corrosion, which was identified quite early, but the answer came a bit late. The mechanism of this oxidation is written here, how the magnetite layer was forming, and then this magnetite layer was getting diffused of soluble species, iron and hydrogen, across a porous oxide diffusion layer, because magnetite occurs in 2 layers. Okay, the lower layer, topic layer, is quite tough and dense, but still the flow hydrodynamics can dissolve it at low temperatures, because at low temperature magnetite is not as stable as it is at high temperature. And then this was the mechanism where Fe was getting dissolved. And you saw the picture, and that picture could give you a good understanding. And this picture will tell you that now what we did is we started adding oxygen, or the first step is we stopped dosing hydrazine or any reducing agent, and we do not want to generate any more magnetite layer, Fe3O4 layer. We now want to generate Fe2O3 layer. Now, where the Fe3O4 is already generated, there what we do is we stop the hydrazine, we let whatever oxygen is there. There are 2 methods, AVTO, all volatile treatment oxidation, where we do not add any kind of reducing agent, it's only ammonia, and oxygenated treatment. In oxygenated treatment, which occurs in all these supercritical plants in India, in oxygenated treatment, we have to add oxygen rather than removing it completely. We first remove it completely, and then we add pure oxygen in it through cylinders. You will see a picture on that, and that is what is now promoting Fe2O3, which is hematite. Hematite is much more stable than what is magnetite. So the whole boiler water chemistry, steam water cycle chemistry changed in last 75 years from magnetite layer black layer where boiler inspectors were very happy to see black layer inside. Now, with the coming time, boiler inspectors would be happy to see hematite layer inside. And this is how hematite layer was getting inside the already formed porous magnetite layer. And this is quite a stable protective layer, even at low temperatures. Now, this is how an FAC will look like. It will get thinned, metal will get thinned, and you see the thinning, how it is happening. And you see a few pictures. Now, in 1997, this was a failure in US in pressure extraction line at Fort Calhoun. And this was the wall thickness, which reduced from 10 to 1.5 mm on feed water piping in Miami. And this was again in US in 1991. So it is actually happening since 1986. And slowly, now people are converted into oxidation treatment, AVTO or OT. Now 70% of NTPC plants have recently in last 2-3 years converted into AVTO, and most of the supercritical plant except 2 of them are in oxidative treatment, and others are in still AVTO because they do not have good plant load factor to run. And this is the tolerance and benefit between oxidation, OT and conventional treatment. You see the benefits which are increasing from phosphate treatment, TSP and NaOH only, or equilibrium phosphate treatment, oblique phosphate treatment. Then EVTR came where ammonia and hydrazine were only dosed and there was no phosphate. Then EVTO, where only ammonia is dosed and nothing else. And then come OT, where a bit of ammonia plus oxygen is being dosed. And this is how the conditions became tighter, the feed water conditions become tighter. Here in phosphate treatment, we required tight condensers, then we required low air in leakage, we required condensate polisher as we went upon to AVTO, and then with oxidative treatment, we don't want any copper alloys in it. And the elimination, with PT, we tried to do the hideout elimination. With AVTR, we tried to do fewer chemical cleanings because number of chemical cleanings was very high when we were dosing hydrazine and phosphate both. And then it went on in AVTO. There was almost no cleaning for 10 years. And in oxidative treatment, fantastic, it's running fantastic. So, for example, I'll give you that we were running a plant in Mundra where we were getting iron in our feed water system, in our boiler water, because that was single phase, drumless boiler. That was a drumless boiler, so that was a one-through cycle. And in one-through cycle, we were getting iron at around 12 ppm to 13 ppm, 12 ppb to 13 ppb, not ppm, ppb, 12 ppb to 13 ppb in our feed water systems and all. Then when we changed it to oxidative treatment, those ppb level came down below 2. So the corrosion which was occurring came down from say so high, from 12 ppb, 13 ppb to 2 ppb. So that is the change which has happened, which has occurred into steam water circuit. And here is the dosing points. Here is where oxygen is getting dosed after CEP, after condensate polishing unit. See, the CEP is condensate extraction pump, and then CP is condensate polisher, or you call it CPU, condensate polisher unit. After that, you dose oxygen. For drum units, it is 30 to 50 ppb, or from one-through units, it is 30 to 150 ppb, and some ammonia. And earlier, here we were dosing ammonia and hydrazine. Now, after deaerator, we are again adding some oxygen, because deaerator, if the vent is open, then it may remove some of the oxygen more. Then we need to add some little bit more oxygen, and then it was going through. Earlier, the iron was being maintained more than 5 ppb. Now it is 0.5 ppb. So the corrosion has reduced a lot in the system. Now, advantages of OT is reduction in boiler chemical cleaning frequency, reduction in boiler tube failures, lot of reduction in boiler tube failures in fact, and reduction in pressure drop in burns through unit, control of single phase FAC. You know, reduction in boiler tube failure means every failure used to lose 4 or 5 crore rupees. Every failure needs a shutdown and repair, and that was equivalent to 4 or 5 crore rupees. That was reduced by advantage of OT. Then control of single phase FAC was done, flow accelerated corrosion was done, and reduction in polyester regeneration frequency was also seen with the oxygenated treatment. Now we go to the next. This is the after cation conductivity, which is now being used in all of the plants. I saw it when I joined in 1999 the company known as Powergen, which was in UK. Powergen, I saw the cation conductivity measurement first time there. No, they were not relying on any of the measurement in the lab being done, and they were just having 1 or 2 chemists in the big large power plants, and they were just cross-checking the online measurements, whatever was happening. And this is one of the systems which they were using, which is known as cation conductivity, and in large form it is known as after cation exchange conductivity. Silent from the DM plant. So this is just there's a thing that if there is some anion present in the water, some kind of contamination coming either from condenser leakage or from feed water or from your chemical addition, then this will catch. Okay, this will catch into the ions. Sodium will be caught and chloride will be released as HCl. So there will be a sudden jump, a sudden spike in the cation conductivity, which will actually indicate that there are some contamination in the water. Now, if there is a contamination, then definitely there has to be some source. That source has to be identified. So now these cation conductivity measurements are always done after the condenser, and in supercritical plants, it's all over the whole one-source system. All over the whole one-source system, we have cation conductivity measurement. Steam, condensate, after CPU, after condensate polishing unit, in the feed water and all. This is the development, and in this development, one more development happened is coming of degas cation conductivity. Now this degas cation conductivity is actually removing the effect of CO2 also. Now cation conductivity was removing the effect of ammonia present in the water, or ammonia and hydrogen present in the water. It was removing it. Now these degas cation conductivity measurements are removing the effect of carbon dioxide also. Now, even when carbon dioxide is being removed, then we know whether this water is actually at what cation conductivity, at what conductivity. And we will know what is the impurity going on. And we will also know whether CO2 is making the cation conductivity high or not. If CO2 is making, then we have to see the source of CO2 also, because air in leakages can cause high CO2 in the system, or if your DM tanks or condensate polishing condensate storage tanks are not doing good for removal of CO2 during water lifting and water supply, then CO2 can enter into the water system. And removal of CO2 from the system is tough, because CO2 will react with ammonia and the water will become ammonium carbamate, and ammonium carbamate is difficult to get removed from the deaeration system. So when we know that yes, this conductivity is contributed due to CO2, we'll try to see the source. And there are further improvements in this. And then this degas conductivity is further, this measurement. Now you see this picture here. This is normal cation resin, which does not tell you anything even if it is exhausted. Okay, we have to check the exhaustion and then we have to change the resin automatically. Now, a new thing has come recently, which is color changing resin. Now, these color changing resins are used in SWA system, steam water analysis system, and when they are regenerated, they are greenish or purple in color, and when they are exhausted, they become red. So we chemists can instantly recognize that, yeah, this needs to be changed. We tell C&I people to please isolate the system, give us the column, we will change the resin and give that to them. This is how this development has happened, this advancement has happened. Then in coal sampling, I'll go a bit faster now because earlier what we were doing in coal sampling is here. Okay, I'll turn the mic up again.
Sample collection. From railway wagons, coal samples are collected by dividing the whole rig into sublots. The wagon numbers are selected according to random number table taken from Clause A 2.1 of BIS standards. Let's suppose that this rig contains 58 wagons. According to this table, we will have 6 sublots. Start with the number from 1 to 10. Follow one direction. If the number encountered is greater than 58, go to the starting number and follow other directions till all the sublots have at least one number. The sampling spot is labeled for an area of 50 centimeters into 50 centimeters. 25 centimeters of coal is removed from the top surface of the selected spot. 50 kilograms of sample is collected from each selected spot. In case of road sale trucks, samples shall be collected from every 8th truck after the truck from which the first sample is collected. The top of sampling spot is leveled and 25 centimeters of coal is removed from the surface of the sampling spot. About 30 kilograms of coal samples shall be collected from the truck selected for sampling. Stones or shales of more than 250 millimeters size shall be removed. The quantity that passes over the conveyor in a day
Now you go into this picture. You see the overhead electrical lines, right? And you see the people, on the top of the rig, so it is an unsafe condition. And plus, in the next, it is said that 25 millimeter of sample, the top from has to be removed. The 25 centimeter is removed from here, on the top, and then taken sample. So it was taking time, 1, it was manpower intensive, 2, and it is also unsafe, 3. So the newer systems now has got a great advantage. You see a video on that. In the newer systems, that is known as auger, okay, which has got either a stationary auger, which can do the sampling automatically within 90 seconds, and that is not unsafe, and you will get sample from the mid-bottom of the vessel or truck, wagon or truck. This is also applicable to the wagons. Now this is known as auger, and which pulls the coal up from the mid of the wagon, because on the top the moisture level is less, and when moisture is less, that means the GCV which is going to show will be high. We'll see a video. I'll keep the voice right now like this only, because this is having other voices inside. I'll just run the video. See, this is the auger we are talking about, and here how it works. You don't have to put any manpower. The place should be wire free, because there should not be any overhead wire going on here. And now it is getting down. It is now getting inserted. All these are made by me only, and my friends. And we have the edge over the foreign makers of auger. Foreign makers has 50 mm size of auger, while we have 250 mm size of auger, because our run-of mines gives very high size of coals. So this is one of the kind which we do, and now we have made some improvements. We can attach a bag to the top of the auger, and though this auger is present, earlier people were importing it from China and selling it within India. Now we and a company called Mitra SK, we are making these augers ourselves. This is a small engineering marvel which India made, making India system. And it is made by engineers, tested by chemists. Happy Engineering Day, Engineers Day. And now he is putting the bag. We'll go front and see how this bag is well fitted. Yes, this bag is fitted. Now he's releasing the coal by rotating it in the opposite direction. Coal is filled. Now we have sample within this. And this whole sampling process took only 90 seconds. So this is another advancement, and similar is in a static truck sampling. You can please see, because one of my friends, Mr. Amit Ashok from Anirudh telemetry system in Mumbai is making these systems. And these are the recent advancements which we are doing. And this is also a mute video. Coal truck information is recorded. Coal drives in, because this can evade the theft from the system, because bad coal can be evaded, and if they have online measurement of ash and moisture, then it's very good. See how it is measuring the whole system, whole area, other things, then finding the points of sampling. Yeah, here. Then he makes the points of sampling, and then it samples. Big and small bridge move, train moves, it samples, it takes the samples up. And then releases the sample into a chute, from where it goes into automatic sample preparation area. So this is how it travels then through a conveyor, and then conveyor takes it to a grinder, roller, and other things, where first iron particles are removed, and then it is getting grinded. And we can talk about more of this when we talk about coal preparation in our second this kind of meeting which Jabalpur Engineering College would be arranging soon. Now, the part here, what is the difference between the manual sampling and the automatic sampling which is made in India now? It was very unsafe because there was a fall from height kind of unsafe condition, and also there are sometimes overhead lines which they may switch off, but if they keep, by mistake they keep on, then a person would get a fatal incident may happen. The sampling was dependent on human personal skills. It was labor intensive and it was taking time. And it was surface sampling where the moisture level could be low. Now it is depth sampling. It is safe. There is no manpower involved on the top of the truck or the wagon. It is completely unbiased. Sampling is from depth and it can optimize manpower as well. But we do not actually want to optimize the manpower. We want to skill him to operate this machine here. Incline, 1 or 2 per persons are available. Though this one also requires 2 persons, but the time taken is much lesser than what it was taking earlier. And this is now being added with a sample preparation room and sample analysis room in these days. And there is a sampling from conveyor. Now earlier a shovel was used to take the sample from the conveyor, maybe a cross belt sampling or stop belt sampling. So, and a cross belt sampling was looking like something where shovel has to be moved on the belt. Belt may be stopped, may not be stopped. And now these auto samplers have come, and since it is 2:30 almost, may I be allowed to continue another 15 minutes, ma'am? Ma'am Kanchan Kare or ma'am Shilpa Kare, if you can answer. Are you able to hear me, ma'am? I don't know whether they are present or not, but still, anyway. So this is a cross-belt sampling system, and if I run this video, then it will take a bit of time. This is about 4 minutes video. Okay, I am muted the sound. You just see what is written over there. The system overview. How does it look? This is a auto sampling and auto sample preparation system, and it prepares the sample automatically. There is an arm which will go into the place where this coal is falling in, and that will collect sample and put in the chute. So this arm is going into this, which is known as sampler spoon, which is having its own encrypt as per ISO, ASTM, or IES specification. We can alter it. This is the crusher which has to crush this coal, whatever is coming in, and then there is a automatic mixture which will mix this coal, and then we'll have a place, the slide gate and the powder cylinder, and it will convert those things back into a sample place where a sample can be held. Then this is the online GCB and ash and moisture analyzer, which is being used into coal beneficiation plant, and wherever coal is being beneficiated, or coal beneficiation means washeries, in fact, where coal is washed and then supplied. So in them, the coal blending is required. For the coal blending purpose, this kind of online systems are required, because telling exact GCB through lab, it takes at least 48 hours because of the moisture, surface moisture and inherent moisture content analysis. So this kind of system of online GCB, which contains X-ray path, which is having a radioactive source in it, can tell us and near accurate but approximate GCV with the ash content and its moisture content. This is how it goes. And lastly, the thermogravimetric analysis is one of the system where if we are a very big, very huge plant and we get a lot of coal samples a day, the proximate analysis can be done through this thermogravimetric analyzer where 24 to 50 samples can be taken in, and ash, moisture, fixed carbon, all these things can be, ash, moisture, volatile matter and fixed carbon can be find out, and this complies with FDA mandate as well. So this is it. Now it's question and answer time, and I give the presentation back to ma'am.
Hello.
Yes.
So all the participants, if you have any question, then you can write it in the chat, and we'll ask one of them at a time.
Okay, if we attend the chat box, then Ms. Chandni Pathak had some.
No, she just put the information. If somebody has a question, please write it in the chat. Okay, so as the participants are maybe they're typing the questions. I hope they have some questions.
Yeah, I also hope so.
Yeah, so in the meantime, I think we should thank Mr. Soumitra Banerjee for his enlightened talks about today's topic. And I have, sir, one question. So I am interested about your work on nanofiltration. So in terms of nanofiltration and ultrafiltration. So if you see when we move from ultrafiltration to nanofiltration, of course we have a better separation. However, one need to probably has to compromise with the flask, so the output.
Yes, maybe.
So,
but
how do you compromise between these two challenges? Can you tell something about that?
See, these are two different membrane technologies. Okay, ultrafiltration and nanofiltration. Now, ultrafiltration only removes suspended solids, maybe up to 0.1 micron. Okay, while nanofiltration is not only removing suspended solids, but it is also removing divalent and multivalent ions like iron, like silica, like your aluminium. No, these calcium and magnesium, mostly calcium, magnesium, aluminium, iron, these are getting removed into nanofiltration. Now, these are two different technologies and having two different rejection rates. Nanofiltration can be worked out up to 85%, while ultrafiltration, we can go up to 92% of recovery rate. But these are two different technologies. So, when we talk about separation, one is separating only suspended solids, but other is not only separating suspended solids, but also removing the hardness salts and iron and aluminium. Is that okay? The answer
Yes, absolutely, sir. Absolutely, sir.
Dear participants, tell me one thing. Now is still my screen is visible?
Yes. Any doubts, please ask.
No, you can remove my screen and put the big screen then for the participants.
Okay, so.
Now I will do it.
Yeah. So I think everybody can see you. Okay. So dear participants, do you have any other questions? You can maybe, if you are not willing to write in the chat, you can unmute yourself one by one and ask our speaker, Mr. Soumitra Banerjee, the questions.
Now, if there is no question, then I understand only two things.
No, sir. I have one more.
I'll just put a joke in between here, small joke. Now, me and my friend, Mr. Bhattacharya, when I was working in Tata Power, we both were invited to Bhubaneswar for one environmental meeting, environmental seminar. We went there, but I was not understanding lot about the technologies, and my colleague who was understanding a bit. So we were just listening to it, trying to understand. Then somebody, the convener came to me and asked, "Sir, how is the program?" Then I said, "Okay, the program is okay." But my colleague immediately said, "It's the effectiveness is 50%." Then he asked, "How 50%?" Then he told that the person who was trying to give the information was giving 100%, but we were not understanding anything. So 100 divided by 2 is 50%. Is that the case here?
I think so. I mean, at least to me.
Okay, that's great.
Okay, so sir, I have one more question. If the speaker doesn't, if the participant doesn't have a question, so you, sir, mentioned that nanofiltration is good for removing suspended particle as well as divalent or beyond that. So I was just wondering, can't we use it for example, desalination of the seawater nanofiltration, because it's mainly sodium chloride?
No, sodium is a monovalent atom, it cannot be removed.
Okay, by nanofiltration.
Yes.
Okay, so in that case, I have seen some publications recently about layer by layer assembly. It's a very modern technology regarding nanofiltration. So in that case, people generally take the ultrafiltration as a support, and then they do alternating layer of polyanion and polycation to make nanometer thin films. So they are claimed that with this kind of film they can use it for the desalination of water. So
yeah, they are using polyamide layer with 0.01 micron and 0.001 micron pore sizes. Okay, that is there.
Okay, so it's possible with the proper modification.
But ultrafiltration is only removing suspended solids, nothing else. Okay?
No, I am talking about the ultrafiltration as a support, and then make a layers of.
You know what is the fact? The fact is all the membranes are similar. We have to make precision pores in the system by machines. That is why ultrafiltration element, RO element costs only 30,000 rupees, while ultrafiltration system costs 120 lakhs. 1,20,000 rupees. Okay, the same element. You understand? So
yes.
we can. I have a specific training program on membrane systems and different this thing, but still, we are lagging behind in India. We need to produce this polyamide ourselves. Unless we make it, we'll be dependent on either US or Europe or China.
Okay. I think if the speakers or if the participant, if they have any question, that is your final chance.
Mr. Anil has unmuted. Mr. Anil has unmuted. Yeah,
yes, Mr. Anil. Yes, Mr. Anil, we can hear you. Okay, so before I move on to Dr. Silpa Saxena for the vote of thanks, I would like to tell all the participants that we will be sharing the feedback form within few minutes time. And please make sure you fill the feedback form in order to get eligible for the certification of this course. Without the feedback form,
Dr. Aditi wanted to say something? Unmuted? No.
okay, so I think we should move on. These are so I move on to Dr. Silpa Saxena, who will give you the vote of thanks.
And I please one request from the speaker. One request from the speaker that I also want to hear from Madam Maheshwari, Madam Anubhav Maheshwari, because she had been my inspiration since my college time, because she only inspired me to go to an industry and learn how the things work.
Okay, thank you so much, Sumit. Thank you for delivering a lecture. Hereby, I would like to say that respected Principal Sir, Dr. A.K. Sharma, Dr. S.K. Srivastava Sir, HOD Applied Chemistry, Dr. Rajiv Chandak, TechUp Coordinator, Dr. Shelga Shukla, TechUp Nodal Officer, Dr. Anubhav Maheshwari Ma'am, Convener of the program, and the learned speaker of today's webinar, Ms. Mr. Banerjee, and the esteemed participants from various academic institutions and industries and their students. I feel extremely happy to propose the vote of thanks on this one-day national webinar on recent